was or run it down. So if you know somebody, let me know.
Yeah.
All right. Thanks.
Could be Bob Savan.
Bob Savan. Somebody threw a name out there for Bob Savan.
That was Dave.
Yeah.
Is Bob a drink collector?
Yes.
I'm going to put my email address out on the chat to everybody. If you can send me an email with his contact info. Oh, that was not me.
Wasn't me.
Not it.
Oh boy. It's 9 o'clock and I'm starting. Somebody already started before me.
It's perfect.
Oh, they just finished.
That's true. I hadn't thought about it that way. And I thank you very much. You did a nice newsletter. I appreciate that. We're trying to add more and more content to it. Every time we look at this, we're looking at a couple other different options. If you would like to see something on that, please send me a note at president@ncar.net, and I will make sure that we do something with it. Again, with all our reports, the minutes, the rest of the stuff was on that. Did anybody have any questions about it? And is everybody getting it? Mike's saying yes, but nobody else is.
Was it supposed to be coming on email or is it snail mail?
Email.
Sent
We're not going to
email a couple of days ago.
It's
Was it
not
the same
snail
time
mail.
you sent out, Darren?
No, it came out just before mine, I think.
And you're sending it out
I
directly.
sent it out Wednesday evening.
Yep, I sent it out to the members at NCRC email distribution list. And
Oh,
I
yeah,
sent-
it came from Ann.
Yep.
It was straight out from Ann because I think I got it right here.
Okay.
There you go.
Yeah, I got it too.
Yeah, I think I got added to the mailing list after that. So I don't know if it's possible to re-forward.
Glenn, do you want me to forward that to you?
Yeah, if you don't mind, Darren, that'd be great. Thank
Okay, I'll do that.
In about 5 years, Glenn, that'll be worth a lot of money.
you. Okay.
Don't believe that. Ann does a great job. She does 10 times the job that I do. Thanks, Terry. I see that.
I would appreciate input from or articles or comments or news bits from anybody who would like to contribute, please.
Well, thank you for doing it, Ann. I appreciate it. It's good.
For suggestions for new types of content.
Yeah, exactly.
You know, kind of like the idea of putting new licensees in there as a new column.
Yep.
We also go outside and look at what other clubs are doing too. LRA doesn't have, well, LRA's got one, but it's, but Longmont, we look at theirs and things like that. And then I go out on the web and see what else they got. One other thing we're going to bring up, as you folks probably already know, that we do a lot of testing lately. And what we decided to do is actually, we're with their permission, we're going to take these people's pictures and actually put it on the newsletter too. So they can get, and this is upgrades or whatever else they do. So we have a test session on the 23rd, and Darren, I believe it's all full, right?
That is correct. It is a full session.
Okay. Last time we talked, somebody had dropped. So.
Well, that drop, I think, took it from 6 to 5. You know, we've only got a max of 8 anyway, so it was still relatively full.
So, okay, we're good to go then.
We're looking probably at another session about 2 weeks later, first or second week of October. I don't know if anybody on the session here is interested or has opinions on what day of the week or a weekend to hold a session.
I've got 2 kids that are interested and might be ready by that time.
Okay.
Any day of the week or weekend that works better or worse?
Doesn't matter, I don't think, for them.
Doug,
right.
we have two sessions at 5:30 and a 7 o'clock session. And we only take 4 people,
Right.
with masks. And Darren is quite a stickler on that. And I appreciate everything he does with that, because I'm a little bit afraid of this stuff myself. Me and Mike, right, Mike? LCK.
Oh, yeah.
Wake up. Any other questions or comments about the newsletter or any of the content that's on there? I feel that this is a better way to go, and then we don't have so much stuff, and then we get right into our presentation, which is more important than anything else. TechFest updates, kind of go through that really quickly. The Hamfest, of course, has been moved, not canceled, possibly moved to the middle of summer. However, due to COVID. However, that I think it's January 16th, and I could be wrong about the date. It'll be the same club meeting we have. We will have a Tech Fest, which anybody, you don't have to be a member. You can do, there's no charge for this. You can go right in there, and we have a whole bunch of things that you can actually attend via Zoom, and more information on that as we go on to it. A week or so ago, I was at the Golden Corral because I wanted to see Sarah. And if you don't know who Sarah is, her and Jonathan are the owners of the Golden Corral, and I wanted to make sure that she knew that we would come back when it was healthy to do it, I guess you could say. And she said, well, you can come now, but I didn't really care for the setup that what they have. What they've got is, it would be okay if everybody was a family. Okay. You could sit 6 people at a table, and they would be fine, because the other one is like 8 feet away at 6 feet. But in our case, we don't know anybody. So I didn't feel it was right to basically put herself under that thing, and it probably wouldn't have been safe in some case, or nothing. So anyway, but we will go back, and she's more than happy to have us. And for your information, anybody's interested, with my dog barking in the background here. The veterans administrations or the vets that were there are not there either. Right now, they're not doing breakfast. If you wanted to go and have breakfast there, I'm sorry, they wouldn't do it. Will they start? It wouldn't possibly be there until the first of the month, the first of the year, if then. Right now, he said that we just don't have enough people that are showing up for breakfast to make that happen. Okay, Red Feather Project update. There isn't any. I've stayed away from that because the people that I would talk to are the Forest Service and the county, and they're busy enough with the stuff that's going on. So I basically kind of stayed away from that. I still have my contacts, but I don't think they want to hear from me right now. Okay. Any questions about any of that? Okay, I'm going to turn this over to Darren, talking about the November Rosin Core project.
All right. Let's see. So first, actually, wish I'd have read the agenda first, and then I would have it in front of me. But we're going to have another Rosin Core class. It will be Friday morning. Unfortunately, that's the only time that the senior center can accommodate us. And I don't have it on this calendar. I believe it is Friday the 6th. Joe, can you check that?
Yes, it is.
Friday the 6th, yeah. And what we're going to be doing is doing a project to build, take a couple of slinkies, some pipe fittings, and paracord, and turn it into a tunable HF antenna. So it's kind of an interesting little project. We've got a cost of $15 on the class to cover the room and all the materials. So I encourage anyone that is interested, if you could sign up. It's done through the City of Fort Collins Recreator Program. And if you need any links or information on that, let me know and I will get that to you. I've already had a few people interested in it, and I think we can manage to get enough people together to hold this one. Any questions?
What antenna will you be building?
Slinky antenna.
Oh, okay.
Basically, you take two metal slinkies, and that way you can tune the length of the slinky to the band that you're working.
Very good.
So it actually kind of works out reasonably well. It's not the best antenna, but it's an interesting antenna, and it does work. Very compact.
Not bad.
All right. And then I guess it's back to you, Joe.
Okay. Kind of make everybody aware, if you hadn't heard, there is, I got to look, Route 66 is still going on till Sunday. If you don't know what that is, there's 21 stations all over the United States, and they will, all you got to do is have one, and you can go put in for a certificate and things like that. And I really enjoy these special events, things like this. This one's been going on a week, and one of the biggest sponsors of it is Bob Heil. So if you're interested, they're on HF. They're doing everything. They're doing sideband, doing FT8, FT4, and CW. So if you're interested in any of those things, just jump on DX Summit or DX Heat and take a look at where they're supposed to be at. I've got all but 5. I got one last night. It took me 2 days to get it. And but they are on FT8, which is about half of what I've been doing. So because the bands have been not so good.
You think?
Go ahead.
Not, you don't think so?
No, I know so.
The bands have been horrible.
Actually, this morning, 40s opened up, surprisingly enough. But speaking about the bands being bad, Terry, tell me why. Good segue.
Okay, well, let me try that. Let's see. I'll get this going here. See if I can share my screen, and if anybody can see it. That desktop share, and so I can get presentation. I'm going to stop sharing. Hold on. Get this. And Zoom. I just go here. Why in the world is that not showing? Here we go. Can anybody that?
There we go. It says your network bandwidth is low, so it might be slow switching slides.
Yeah, I can't see anybody's picture here, so it's complaining to me my bandwidth is slow. Well, all right. Well, the reason the bands are bad is this thing called the ionosphere. It's just not supportive of communication, and there's a lot of discussion about what sunspots are and what they aren't, and I'm going to tell you what I know about it. So page 2, the outline, I'm going to discuss the Earth's ionosphere, sunspots, solar cycles, and how to deal with it. Is me across okay?
Yeah, it just popped up. Looks good, Terry.
Okay. Give the slides a little bit of time to pop up. So if you could see the ionosphere.
Terry, could I interrupt for just a second? Does it help if everyone turns their mics and their videos off? Will that help at all?
This I don't.
Darren, do you know?
Unlikely.
I think what would actually
Terry's
help,
got
Terry,
his video off, and that's about the best we can do. The only other option would be if somebody else did the slides.
yeah, if you're able to send me the slides, Terry, I can share my screen, and then all you have to do is talk and tell me when to change slides.
Dave, we've got the slides.
I sent Joe the latest copy. So the slides you have like a little on me.
Yeah, you're breaking up pretty bad. Joe, do you have them handy there to just take over running them?
Let me check. I'm sure I've got them someplace, but Where would be a question?
Yeah, the ones I sent a couple days ago had some errors in them. So
Oh,
the one I just sent this morning is the right one.
I didn't get anything this morning.
I did not either.
Joe or Darren,
Yes.
Yes.
I've had this problem before, and for some reason the video is satisfactory, the audio is not, and I've used the dial-in number and mute the audio from the internet, and use the dial-in number to bring in the audio.
Well, I've got him here. I've got the old ones though, Terry. That's all I've got.
It's just some spelling issues that I think we can work with that.
No, there's a couple errors I made in the physics. So there's some statements in the old presentation that are technically wrong.
Well, I got the PDF. If
So-
maybe you want me to take it.
Terry, if you can just go to the chat window and there's a file thing. So drop down to my name or the YouTube feed name and throw a file in there, throw them in there, and I can share the slides.
All right, hold on. I'll share my screen here. Chat window. Oh, does it have a file? Oh, okay, so I can send a file. Personal. Okay, I shared that one with everyone.
I am pulling it up right now.
I've
All
got it up as a PDF.
One of the two of you. I'll let you arm wrestle for it.
I thought the hotel bandwidth would be better, but I guess not.
Is that working?
Can you go to like a full screen or something there?
Is that any better?
Some kind of presentation mode.
It's a PDF.
It's a PDF, so there won't be a presentation mode.
Yeah, but I thought there was like a view one page at a time or something.
Yeah, I don't see his menu bar, but you're right. There should be.
I don't see anything that even make as a PDF. I can do this. That's pretty much all I can do.
Well, I suppose that'll have to work.
Hey, Terry, where you want it?
Go back to the picture of the globe. Page 3.
There you go.
Next to the recycle at the top, you can enlarge.
Joe, you can click on the plus in the menu bar that you got immediately above the slides. There you go. And then slide up and down to fill the screen.
I'd get a little smaller than that.
Yep, you got it.
That work?
Yep.
Yeah. So, hey, actually, I'm starting to get pictures in now. Okay, so this is what the ionosphere would look like if you could see the ionospheric plasma with your eye. It's a layer of the atmosphere, a thin shell around the Earth, and it has variations. It tends to be denser at the equator and lighter at the poles. And there's some reasons for that. You go to the next slide, please. These are the basic physics processes that are involved in producing the ionosphere. It's extremely simple, right? Yeah. There are external forcing functions from the sun. There are internal forcing functions from the lower atmosphere. And then the ionosphere has a physics all its own. So it behaves in particular ways, even if you leave it alone. It has some effects, and it interacts very strongly with the Earth's magnetic field. And they're both ions and neutrals in a plasma, and sometimes they go the same direction, and sometimes they go opposite directions and make currents. And it's just a very, very complicated weather system, which makes it difficult to predict. We go into the next slide, please. So this gives some view of the kinds of variations you can get in the Earth's ionosphere. The top panel is sort of on a global scale. You can see that there are enhancements around the equator, depletions around the poles, day and night. Nighttime's right in the middle by Africa there. And then the ionosphere tends to bifurcate, have these two lobes in the equatorial region, and that's due to the way the forces in the magnetic fields work there. In the lower left-hand corner, you can see that even on a continental scale, that there can be sharp gradients in this ionosphere just on a normal day. And on the lower right-hand side is an example of irregularities that can cause radio scattering. And these are irregularities down to meter scales. So the ionosphere has scale sizes all the way from global down to meters. Next slide, please. So what is the ionosphere? It occupies the same physical space as something we call the thermosphere, and that's the unionized upper atmosphere. The ionosphere is a plasma of ionized atmospheric gases, constituting mostly from the ground up nitrous oxide, oxygen atoms, oxygen molecules, hydrogen, and helium. The ionosphere is produced mostly by solar extreme ultraviolet, EUV, and we'll get into that a lot later. And that's mostly because there are some particles that come from the sun, but those don't play a major factor, particularly not at solar minimum. The ionosphere exists at an altitude from about 50 to 100 kilometers of altitude, and it has strong time variations, both daily with the season and with the 11-year solar cycle. And there's strong interaction with the Earth's magnetic field, and it has a lot of forcing from below. And the picture there shows you why the ionosphere forms layers, because as a function of altitude, neutral density is increasing. So you have more neutral atmosphere to ionize, and then you have a radiation intensity that's being absorbed by that neutral density, and it decreases in altitude. At some point, the two meet, and that's a balance where you get the maximum production rate. And that's the reason why the ionosphere has layers. And that radiation intensity is the extreme ultraviolet. Next slide, please. So here are the kind of density profiles. If you've got your general or extra class, you've heard about E regions and F1s and F2 layers, and these are examples of the layers. The E region between about 90 and 150 kilometers. D region below. D region is mostly for absorbing, absorbs your HF energy. The E region sometimes reflects if you have the right conditions. There's an F1 layer, and the E and the F1 only exist in the daytime. And then there's the F2, which is up around 400 or 500 kilometers. And a little thing on the scale on the right is that only things below the peak density control HF propagation. Everything above that, once your radio wave gets above that, it's already on its way into space and never comes back to Earth. Slide, please. So this extreme ultraviolet, let's talk about that a little bit. That's an important factor in what's going on here. EUV is just light of extremely short wavelength, about 10 to 120 nanometers. The visible light's around 500 to 600 nanometers. It's generated in the sun's chromosphere. It's a layer of the sun. We'll talk about layers of the sun soon. The amount of UV varies quite a bit with the solar cycle. Very much unlike the visible light. The visible light from the sun is very, very constant. And that's what kind of makes our weather fairly constant. The ultraviolet light changes dramatically with the solar cycle. The ultraviolet light creates the ionosphere by the process called photoionization, as shown in the picture. If you have a oxygen atom or molecule and you hit it with a photon, h nu, that energy for the right frequency, the right wavelength, the photon will ionize the oxygen into an electron and a positive ion. In the process, that photon is absorbed. It has put its energy into the ionization process. And so the upper atmosphere gases, like the nitrous oxide, NO, form the D and the E layers. The oxygen molecules form the F1. The oxygen atoms form the F2. And then above that in the top side, you'll get the hydrogen and helium being ionized. And that's another reason why the ionosphere has these different layers to it, because different photons, different molecules absorb photons of different energy. The extreme ultraviolet is generally a smooth illumination of the daylight hemisphere. It's fairly smooth, with some exceptions we'll get into. And like all light, it goes away at night. So the ionization stops in the daytime, stops at night when the sun sets. Slide, please. So here are some different pictures of the layers of the sun. The internal layers are really wild guesses. We don't really know a whole lot about that. The layers we can see are the chromosphere, the corona, which is what you see during a solar eclipse, and the thing called the photosphere, which is the visible portion of the sun in visible light. And these sunspots that we're going to talk about are in between the photosphere and the chromosphere. And this is sort of an orientation that shows the different layers of the sun. Next, please. Sunspots, what are they? They're relatively cool areas of the sun. They're about the size of a planet, a little bigger, a little smaller. They exist in this photosphere of the sun. And their properties are they have radial magnetic field lines. And those radial magnetic field lines allow more ultraviolet light to escape the sun's surface. And they're related to these things called prominences, which is a picture in the upper right-hand corner. And the prominence is like a big bundle of magnetic field lines that contain a lot of energy and a lot of plasma. Those prominences are the sources of solar radio noise bursts. I don't know if anybody's heard of that, but every once in a while, these prominences collapse and they emit a lot of energy, from X-ray flares all the way down to radio waves. These sunspots are the sources of solar flares and the coronal mass ejections that are associated with them, and they're easily visible. You can see them with just a pinhole camera and white light, but you can see them a little better with a hydrogen alpha filter. And I say the word sunspots is probably one of the most misunderstood terms in amateur radio. People blame a lot of things on sunspots, but this is a technical detail, what they are and what they do and what they don't do. And almost as bad as the way hams throw the word ground around. All right, it means a lot of different things to a lot of different people. So the next slide, please. So this is how sunspots and magnetic fields are aligned. They're formed by this convection layer at the bottom of the screen. You see these little rotating circles. The lower level of the sun bubbles like a pot of boiling water, and you get these convection cells. And those interface with the next layer up, which is the chromosphere, the photosphere, sorry. And that's where the sunspots tend to exist. And those magnetic field lines allow more light energy to come out of the different sunspots. And it also has those curved magnetic fields. And curved magnetic fields are a great storage unit for plasma energy. And when it gets released, it tends to be fairly violent. So next slide, please. The other phenomena we often deal with, particularly at solar minimum, are something called a coronal hole. And this is a picture of a coronal hole. I think that's in X-rays. And it's similar to sunspots in that it's a region of open magnetic field lines, allows more UV to radiate, and allows solar particles to escape. And the coronal holes are the common source of space weather now at solar minimum. Slide, please. So the sunspots come in a cycle. And what happens is that early in the cycle, the sunspots tend to form in the equatorial regions of the sun. If you look at that top diagram, that's a diagram of solar latitude versus time. And as you progress through a solar cycle, you tend to get more of them, and they also move toward, or their formation region moves toward the equator. The sunspots don't physically move themselves, but the areas that's likely to form them moves from high solar latitudes down to equatorial latitudes. And the bottom graph is a graph of the sunspot number, and that sunspot number increases. And you can see, we call these the butterfly diagrams. And the north and the south hemispheres are not always the same. So your actual total amount of solar activity depends on the coordination between the northern and the southern hemispheres. Sometimes they form at the same, some cycles they sort of evolve at the same time, they peak at the same time. In other cycles, they have different timing, and the north may peak and then the south may peak, and that's why you get a double humped solar cycle prediction, a solar cycle pattern. Next slide, please. Well, solar cycle forecasts, as I said, like Yogi Berra says, it's hard to make predictions, especially about the future. And I like to say there are three kinds of lies: lies, damned lies, and forecasts, with some apologies to Mark Twain. But everybody and his kid brother has a forecast, and everybody uses a different method, and everybody gets a different answer. And this shows a technical plot of the forecast for the upcoming solar cycle from half a dozen different credible providers. You know, they have a methodology that seems reasonable, but they all give different answers. And I don't trust a one of them. Slide, please. This is from the director of the High Altitude Observatory in Boulder, Scott McIntosh, and he has this unique method of looking at the magnetic field lines and the butterfly patterns of the sunspots. And if you see sort of in around the 2003, 2004 era, you'll see these descending red line and ascending blue line. And those underlying colors are magnetic field activities in the sun. And he's able to track the physics of the sun with that methodology. And you see the sunspots correlate reasonably well to the areas of magnetic activity. And where he's drawn the vertical line is where those projections of those activity levels go to zero. And you can see, if you look at around 2009 or 2010, there's still some magnetic activity near the solar equator while the polar regions are starting to activate. So the actual sunspot number kind of dips, but he's working on this fairly precise method of looking at when the physics change over. And this is a lot to do with the solar physics. And I'm not a solar physicist, but I do play one on the radio. So the next slide, please. This is something people get confused about a lot. This concept of proxies and correlation and causality. You've probably heard of something called F10.7. That's the 10.7 centimeter radio flux that comes out of the sun. And it's a proxy for the extreme ultraviolet that creates the ionosphere. And they are correlated. And the big point is we can measure the 10.7 centimeters with a radio antenna on the ground. EUV gets all absorbed in the upper atmosphere, so you can only measure it by satellite, and satellites are expensive and they're difficult to keep in the air all the time, and it's hard to calibrate them from one satellite to the next. So measuring EUV has been a technical issue. So what we do is we use the 10.7 centimeter proxy, and this is due to the black body radiation, which is proportional to the solar temperature. But the two are not the same. They are related, but they're not identical. And so variations in one does not necessarily mean you have variations in the other. And it's really the ultraviolet that's causing the sun to, causing the ionosphere to develop. And only to the extent that the 10.7 centimeter in the unmeasured UV are the same, that the 10.7 centimeter is useful for ionosphere predictions. But the solar EUV and the sunspots are correlated because the sunspots let out these beams of EUV, and in the process, they also generate radio flares and noise bursts, but those are independent processes. So the sun, the ionosphere can build up due to the UV, but the same phenomena that builds it up also tends to have these solar flares that generate magnetic storms and coronal mass ejections that disturb the ionosphere. So the UV is just it's kind of like the source, a flashlight that just pumps up the ionosphere. But if that's all there was, it would be a fairly smooth ionosphere. It wouldn't have a lot of variations in it. But the way the physics of the sun works is that these same processes that generate the ionosphere also generate these solar flares that make radio noise and these things called coronal mass ejections. And these are ejections from the sun that hit the Earth's magnetic field the way a hammer hits a bell, and the Earth's magnetic field rings when it gets hit that way. And that ringing magnetic field very much disturbs the ionosphere. And that's what creates what we call ionospheric storms that are more popular at, more common at high solar activities than low. But these are different physical phenomena that are working at the same time. And so they are correlated, they're not causal. One does not cause the other. They just happen to happen at the same time. And that gets confusing. So I'm just trying to clear that up. Next slide, please. I like to demonstrate that with the concept of comparing chickenpox to the solar maximum. Chickenpox is caused by a virus. Fever is a symptom of chickenpox, and the pox marks themselves are another symptom. And it's the pox marks, if you ever had chickenpox, are the annoying ones. You want to scratch them and you get all these scars and stuff. Solar maximum, the solar max is caused by the internal solar convection and how energy escapes the sun. The increased ultraviolet light is a symptom, and the sunspots are a symptom. And they're correlated, but they're not causing. And the sunspots are kind of annoying. It makes these CMEs, these X-ray flares, and these solar radio bursts and radio frequency interference. So it's that difference between two phenomena that are related to each other that happen at the same time, but they're different phenomena. They have an underlying cause. And it's only recently we kind of really understood that it's solar convection that causes the solar cycle. Next slide, please. So, as I was often told, you got a problem, become an engineer, build a bridge, and get over it. And that's what a lot of us do. We use data rather than forecasts to deal with our propagation problems. Slide, please. And here's an example of what the Air Force does, example, for HF propagation prediction, is they take data and they create a numerical model of this ionosphere. They use HF propagation prediction called ray tracing to say, given an ionosphere and a transmitter location and a frequency, where does that energy go? And they make a HF illumination map, which is where energy will land on the ground if you key up the transmitter at a given frequency and location. And that particular map was for WWV at 10 megahertz. And it shows the skip zone, and it shows skip zone enhancements and second hops and second hop skip zones and so forth. So that's a sophisticated, data-driven. The ionospheric models are not really forecast models, and they just take ground-based data to make the models accurate, and then they do a propagation prediction. Slide, please. And here's an example of a ray trace. In the middle of the plot, you'll see this thing called EDP. That's the electron density profile. And you launch a bunch of rays from the left-hand side of the plot, and they move to the upper right. And Rays that launch at too high an angle are called penetrating rays. Those escape the ionosphere and go into space. Rays that are below the horizon can't transmit, so you have this thing called a skip zone. Then there's this reception zone, which is around 1,000 to 1,500 kilometers in that plot. That's where most of the rays fall back to the Earth at once. And then there's a second hop further off to the right. But that's kind of example of how your HF energy propagates through this ionosphere. Slide, please. So you can do this yourself by using the source. Slide. And this is the source that many people use, these things called ionograms that I produce, like down in Boulder. And this is a example of how to read the plots that are produced. The green and red points on there are data. These are echo data from a radar system. And the bottom graph is frequency in megahertz. The top vertical axis is range or height in kilometers. And there's a date and a time there. And at the bottom, you will see this thing called an MUF table. That's the maximum usable frequency. This is under the assumption that the ionosphere is the one that you're being measured. And if that's the midpoint of your propagation path, the MUF table will tell you for different distances what's the maximum frequency you can use to communicate for that ionosphere at that time. And this is a fairly accurate methodology because it's based on observations. Slide, please. So another data product I produce is this FOF2. That's the critical frequency. If you want to get to MUF for a 3,000 kilometer path, you multiply by about 3. But that plot shows in green the previous 5 days. Red shows yesterday, and blue would show today if you look at this plot in real time. This shows the effect of an ionospheric storm. That everything had been going along pretty normal. There's a certain amount of variability day to day, shown by the wiggliness of the green lines. And then, boom, we had a magnetic storm, and we had depressed ionosphere values for about 12 hours. And then on the day that plotted in blue, it's starting to recover, and you can see, you could probably guess it would probably be more of a normal day based on the way the blue line has evolved. Slide, please. And so here's an example of how you would use this. If you wanted to do NVIS communication, then the M factor is 0. You use the FOF2 directly to determine the frequency you can use. And here's the 24-hour plot, or a 1-week plot of data with 40 and 80 meters frequencies outlined. So you can see most of the time 80 meters will propagate, but there's sometimes, like right around 13 UT, when the ionosphere collapses just before sunrise, it's going to go away. And at nighttime, it's a matter of day to day. Some days the line's above, some days the line's below. If you're trying to use 40, it's very rare that the density gets up to provide 40 meter communication. So slide, please. This is a shameless plug of a map of all the data that we get at NOAA in real time for any one day. Each one of those circles is a ionoson station, a data point, and you can pull most of them up from my webpage, which I'll give a link to later. Next slide, please. You might actually find this more useful. There's a ham operator, KC2 Golf, who takes all of my data and makes a maximum usable frequency map. Each of the data points are little dots on the graph, and the number in there is the MUF value observed at that station. And he uses a combination of climate model and real-time data to produce these contour maps. And you can see, like, over Africa and Asia and things, we don't have any data. So it's all just climatology. But where we do have data, his curves are consistent with the data. And you use this map by deciding where you are and who you want to talk to, take the contour halfway between, and that should be the maximum usable frequency on that path. Slide, please. And so here's a link where you can get the data from. There's the URL. You can also find it by, if you Google the terms NOAA and Merion, you'll come up with that in the first couple hits. And you can certainly get the latest ionograms from Austin, Texas, Boulder, Colorado, Wallops Island, Virginia, and a few other places. There are these real-time FOF2 plots that I showed, the red, blue, and green curves. And many stations have no data. That's just normal. And this is a stupid, simple web page that allows people easy access to the data because I don't know how to do it any better. So it's a share and enjoy. Slide, please. Any questions?
I have a comment.
Okay.
This is Doug K0DTK. I got this call in Fort Collins in 1956 when I was 13 years old. I loved your chart that showed the overall history of sunspot cycles. Cycle 19 it still remains an all-time high, and I was there for that. I just wanted to tell you guys one story about how fantastic conditions were. That was in the days when everything was AM. Single sideband was a really rarity. 10 meters was absolutely incredible. The one story true story, I heard a guy in Pennsylvania, I was in Fort Collins, calling, just doing test, hello test, and I gave him a call, and he about fell off his chair. He was in Pennsylvania. He was testing a 5-watt AM transmitter with a single 5763 tube, and he was testing it into a dummy load, and he was in S8 in Fort Collins, Colorado. So 10 meters what reflected that all-time cycle 19 sunspot high, and it was the all-time golden age of incredible conditions, and 10 meters was just a phenomenal band. Anyhow, I just wanted to tell you that story. I remember that very clearly.
Hey, Terry, I had a question.
Okay.
You showed the measurements that you take to determine the reflections. How do you actually do that? Because you can't just send the signal straight up. Obviously, it won't be reflected back. I'm just curious, how the mechanics of taking those measurements is actually done.
Okay, well, that's a sweep frequency MFHF radar system. Yes, in fact, we do have vertical incidence transmitting antennas. Most of our energy goes straight up and reflects off the ionosphere at true vertical incidence.
Oh, okay, so it's just a weak return signal that you can measure.
Yeah, well, we've got quite a bit of power behind the radar too.
Okay. All right, thanks.
Sure.
Very quick question. Do you have any issue if I post your slide set to the website and make it available?
No, take the links and make all those available, please.
All right, I will get that posted here this afternoon and make it available to everybody.
The purpose of them is to be used.
I just always like to ask permission first.
Understood.
Terry, I guess I have a question.
Okay.
And I'm afraid you're going to answer. I'm afraid you're going to answer it.
I'll do my best.
You and I have talked quite a bit about this actually on a TechNet one night. I've heard predictions, and again, the predictions are about as good as anybody's, that it could be a bad cycle, could be a good cycle, could be the best ever, or not worth a damn. Do you have any predictions which we will not hold you to?
Well, the one that I understand the best, and is the one that's done by Dr. McIntosh, done at the High Altitude Observatory, which is why I included his slide. And I'd have to go into a lot more physics and mathematics to even begin to explain what he's doing. But he is looking at the physics of that magnetic changeover. And his prediction is that this could be a real boom of a solar cycle. And his prediction is so far out of the realm of everybody else's predictions, they're kind of dismissing his comments. And that's what often what happens in science. When you're an outlier guy, they'll ridicule you. But
Can I summarize that?
yeah, and my partner Justin here is can come on here and explain that. Justin, help me with the slides.
The NOAA forecast is a weak cycle that's going to peak in about 2 years. And Scott's forecast is a very strong cycle, an anomalously strong cycle that's going to start peaking very soon. So they are basically on opposite ends of the spectrum. And I agree with Terry that the physics analysis that Scott has done is more convincing to me than the official forecast that NOAA has put out. That's basically all.
Yeah, I think the NOAA forecast is based on history, and the Macintosh forecast is based on more physics-based. And like I said, there's lies, damn lies, and forecasts.
Well, you said it that Scott, I imagine it's the same one that we know, has predicted this is going to end very soon or peak very soon.
Yeah, his call is for a very, very rapid increase in solar activity starting right around now. Yeah, really starting about a month ago. But that's a very short period of time for the sun. Yeah, right around now is the time that's predicted to start.
And sunspots have been higher.
Yeah.
And I guess I have to ask, how does that, and I should know this, how does that increase, decrease propagation?
Well, the more sunspots you have, the more sunspots are relative to this solar UV that produces the ionosphere. So the UV will increase because the solar activity is higher. And that UV is what makes the ionosphere, that makes better propagation at higher frequencies.
It's kind of what I thought. Well, if it's good now, well, I don't see it good now, but anyway, it's whatever, I guess.
No, it isn't. It's just on the, according to his prediction, is just on the very beginning of starting to rise.
Oh, okay. Okay.
So,
because I think I saw 69 sunspots yesterday, if I'm right.
Yeah, we do have a few more than we had a month ago.
I have a question. This is Bob, N0TZU. This isn't anything that we probably need to worry about in our lifetimes, but I'm just curious, the magnetic field seems to be weakening, geomagnetic field. And my question is, if that were very weak, it would seem that would then not degrade HF propagation when we have storms, since there wouldn't be that much of a magnetic field. But maybe that's wrong. Maybe we would actually have an enhancement. So what is the contribution to HF propagation from just the strength of the geomagnetic field in general?
Hey, Bob. Yeah, the magnetic field, Earth's magnetic field essentially holds the ionosphere in place. We have a comparative planetary study. We look at Mars, who has recently lost its magnetic field, recently in geologic timescales. Mars recently lost its magnetic field. Its core stopped spinning. It cooled down. And that allowed the sun to ionize the Martian atmosphere and the solar wind to blow all the ionosphere away and taking all the atmosphere with it. And that's my leading theory as to why Mars doesn't have much of an atmosphere, is the sun blew it all away. And so if we lost our magnetic field, right now we get outflow from the polar regions where the sun, where the magnetic field lines are open to outer space. And there's a slow amount of atmosphere leakage out of the poles. But without a magnetic field, that leakage would happen all over the place. The sun would blow the ionosphere away and produce more and blow that away and produce more and blow that away. We'd get a much weaker ionosphere.
So since the Earth's had a lot of reversals over time, we know that from the history of rocks and stuff. Clearly, that didn't happen, at least not in any huge sense. So during those times of reversal, there must not have been enough time for the atmosphere or the ionosphere to be blown away, I would guess.
That's my theory too, that during the reversal, the time when we had no magnetic field was probably very short in the in the amount of, in the time scales that it would take. Would take thousands and thousands of years to make any significant decrease in the atmospheric density due to the solar wind and solar radiation. So the magnetic field dropping for a few years probably is not going to reduce the amount of atmosphere on the planet that much.
Okay, and so that's, and just then bringing this back to the present day, for it seems to me then when we have a quiet magnetic field, in other words, very steady, that we get whatever the HF propagation that we're going to get given the ionospheric ionization. But if it's disturbed, then generally we get a degradation. So it seems then that the magnetic field from a day-to-day perspective can really only hurt us in terms of HF propagation. Is that correct?
No, the magnetic field also shields us from the solar disturbances, the solar magnetic disturbances. These are the coronal mass ejections I talked about. That magnetic field acts like a buffer and that keeps the solar energy, the solar CMEs from penetrating down too far from the Earth. It affects the poles, but not so much the equators. Without the magnetic field, these solar induced disturbances would be more global rather than limited to the polar regions. That's inside the auroral zone.
Great, thank you.
Sure.
I have a question. When the high energy ultraviolet hits the ionosphere, are signals reflected off the electrons or the ions or both?
The electrons.
Okay.
The electric field of your radio wave moves the electron. It moves the proton very slightly, but it's so much heavier than the electron, many, many thousands of times heavier, that the ion doesn't move. It's the motion of the electron that interacts with the radio wave that causes it to refract. And that's what causes the bending necessary to bring an HF signal back to the ground.
So it's electron density more than anything.
It is electron density that's measured by radio wave techniques.
I have a question for you, Terry. When we're listening on HF, we oftentimes hear a sweeping signal go from high to low or low to high. Is that one of your ionosounds?
It's unlikely you're hearing one of them if you're listening to sideband. What you're likely hearing is something called a chirp sounder. And those are an FMCW modulated signal of different ionosons that are run by the Navy typically for oblique propagation. My ionoson is it's a pulse signal, so it tends to be more of a buzz.
So follow up on that topic, since we're fairly close here to the Boulder ionosons, is it possible to hear them just routinely on our HF radios?
Yeah, if you can get them on ground wave, the sky wave is usually attenuated fairly strongly. I just live south of you, Bob, and I've hardly ever heard my sounder in Boulder from my QTH. The only time I can really hear it is when I'm up on Table Mountain. I can get direct line of sight propagation.
Okay.
The ground wave attenuates very, very rapidly. And the channel occupancy is pretty small. If you're looking at a single channel, HF channel, it's going to be on for 1 second every 5 minutes.
Yeah.
If you tracked it with a waterfall, that might be more likely to catch it that way.
Okay, thanks.
Terry, I got a question for you.
Okay.
What is the A and the K index? What does that mean?
Those are levels of magnetic field activity that are introduced by the interaction between the sun's magnetic field and the Earth's magnetic field. That's what we call a magnetic storm, is when those numbers go high. And that's like that sun being a hammer, hitting that bell of the Earth's magnetic field and making it ring. And that ringing disturbs the plasma.
So the higher the number I know, the worse it is. The lower the number, the better.
Yeah, the ionosphere is rather unpredictable under high magnetic activity conditions. The physics of it change very rapidly, and it gets torn and blown all over the place. It's a little bit like a hurricane, in that it really causes a lot of disturbance globally. And the higher that value is, the more magnetic disturbance there is, the less predictable the ionosphere is.
Thank you.
Terry, does this affect all bands or the higher bands more than, say, 40 and 80?
No, I don't think so.
In other words, it's across the board, it's all the same?
I think it affects the lower bands more than the higher bands.
Oh, okay.
The lower bands tend to be more sensitive to radio plasma interactions.
Good to know. So stay off of 40, I guess.
And there's some phenomena I've seen when we did the school club roundup. We were trying to help the kids do propagation, and there's some days where we could get really good propagation on 40, and other days we couldn't. And my data did not explain why. I think there's some amount of some days are just some irregularities in the ionosphere that don't show up on my instrument that absorb a lot of HF energy, is my leading theory. But that's just a wild guess.
Terry, along those lines, it's often said that the medium wave bands, 160, for example, have really a much different propagation system because they're using the E layer. Could you elaborate on that a little bit?
Yeah, when you start getting into the into wavelengths in the tens of kilometers, you're in that boundary range between LF and VLF and HF. The lower frequencies, the VLF frequencies, propagate as a waveguide between the Earth's surface and the ionosphere, because that distance is a small fraction of the wavelength. For the AM broadcast stations, the medium wave frequencies, there's almost always enough plasma somewhere to reflect those. And so it's not quite constrained enough to be a waveguide. So waveguide theory doesn't quite work to explain that. And ray propagation theory starts to break down as well, because the wavelengths are so long. So it's not quite a free space environment, and it's not quite a waveguide, which makes it kind of difficult to predict. But the whole business about why you can hear the long distance AM stations is because the disappearance of the D layer at sunset. That allows the medium wave frequencies to get up to the ionosphere, and then they can propagate worldwide.
Okay, thank you.
Just a quick question about some of the apps that you have and things like that. I've got one here, and I can't, what's it called? HF propagation. I guess it's actually just off of MSN's or off of Microsoft's little board there. Can you trust those, or are they just something, whatever?
I'm not sure what you're talking about, Joe.
Well, they have apps that actually talk about propagation.
I'm not familiar with them, so I can't speak to their accuracy.
Okay, because it basically, I'm looking at it now, and it says solar flux is 69, and it basically tells me that the bands 40 and 80 are okay. The rest of it's just junk.
Well, I said there's that fairly loose correlation between solar flux and what the ionosphere really is, because there's all those other physical processes that are happening in the ionosphere that we're not entirely sure about. That's why it's still research. So the solar flux is a necessary but not sufficient condition for understanding the ionosphere. it could be a magnetic storm. There are certain days when the terrestrial weather certainly causes ionospheric effects, and there are times of different seasons. So unless somebody's actually making a plasma measurement, knowing whether a band should be open or not is more a matter of like statistics or seasonality. Just on average conditions with that amount of flux, then that band should be open.
And I would imagine it can alter from hour to hour, couldn't it?
Yeah, it does. The dynamics, we make a measurement every 5 minutes and we see variation on a 5-minute scale. And if you have ever worked a contact, you can tell yourself by how the signal fades.
Oh, yeah.
Sometimes it's rock solid and sometimes it fades with periods of seconds.
I totally agree. I do a lot of HF stuff, and it's right now it's a fight, I guess you could say.
Yeah, we really don't understand the shorter timescale fluctuations of the ionosphere because we're not really able to measure it that quickly.
What does, when someone can't actually talk to you phone or possibly CW, you can get on the digital network and you can usually raise the guy with about a third the power that you could do that. Why is that? Does the ionosphere take it differently, or what's?
The vast majority of the time, that's just because you're changing your signal to noise ratio.
Oh, okay.
The digital modes put less signal into much less noise bandwidth. Was when you're on phone sideband, you've got 3 kilohertz of noise coming into your receiver. But if you're on a digital mode, you have about 1 or 2 hertz worth of noise coming into your receiver. So thousands of times less noise.
That makes a lot of sense.
And there are other scattering phenomena that we're not quite familiar with, because some of these ionosphere irregularities can produce scatter, and these digital modes can often pick up propagation well above the maximum usable frequency. All this maximum usable frequency stuff was really designed for sideband communication.
So I have a question about other sites. You mentioned that you've got some here I'm going to look up later. Thanks for the links. But I also often go to this Australian government site, which has a nice presentation that's useful for me as an amateur. Have you looked at that, and do you have any comments about it?
I do. I'm kind of envious of the effort that the Australians have put in the presentation of their data to the general public. The Australian government obviously has more of ham radio operators than the US government does. Whenever at work, I say, well, this is for the ham radio operators. I get a big raspberry from my management. So the Australians, we have a cooperative agreement where we share data. And oftentimes they're using our data to run and make their products.
Okay, yeah, I wondered about that. Well, they have a huge outback, and they make use of a lot of HF, a lot of mobile HF. I mean, it's a lifeline for them.
Exactly. It's much more important to the Australian citizens than it is to the US citizens.
Hey, Terry. This is John and KZOR. I have a kind of a techie question related to your slide on ray tracing. Way back when, I used to work for the Radio Research Lab at University of Illinois in Urbana, and we did angle of arrival type measurements with a HF interferometer. And just curious if those types of instruments are still in use.
Yeah, in fact, our flagship station at Wallops Island is an angle of arrival interferometer. I've got 8 coherent HF digital receivers on an aperture about 100 meters, and we can measure the phase of the radio wave across the aperture and determine the arrival angle. So, yeah, arrival angle measurements are still quite common.
Okay, thanks.
Any other questions for Terry?
Great presentation.
Yes. Go ahead.
Thank you, Terry.
Terry,
Yeah, it's
thanks so much
great.
for doing. You've really helped me out a lot. It's very good. Thank you very much for doing this.
Yeah, you're welcome. And when I'm home, I'm usually on the 275 repeater. So if anybody wants to give a call out and has a question, I'll be glad to pick it up and answer.
He's normally on the tech net too, on Monday nights at 6 o'clock.
Yep, that's been known to happen.
And he's been a big help to the club and everything else for years and years. So I thank you very much for all your efforts.
Glad to do it, Joe.
Any other questions, comments?
Unrelated to the presentation, Joe, did you want to mention something about the exercise and use of the channels coming up?
Oh yeah, I wasn't going to do it for a week or so, but if you want to, October 3rd at 7:30, there's going to be an announcement come out that we're taking all of the Horsetooth repeaters for an exercise for Aries. Until around noon or so, we're doing this exercise with all of our served agencies. The command group will be on 4475, and I think 115 will be operations. So if you get on that, please use it sparingly. And we'd prefer that you jump over to Buckhorn if you needed to use it. But again, it's only for a couple, 3 hours. And I hope everybody kind of does that. It's an Aries thing that we have to do every year and that we really need to do because with COVID and things like that, we still need to know that we have our OP people. Any questions about that or anything else?
So we'll get off of I-70 when we get to St. Luke's. That's when we turn south.
I think that's on Terry's. So I wasn't sure. One other thing I want to tell everybody that next month, and Ann, this is for you also, Darren will be our presenter. Yeah, over there in the upper left-hand corner, KC0ZIE will be doing ham radio and ballooning, which he's done quite a bit of. Do you care to kind of give us a little taste of that, Darren?
Yeah, it's I've worked with a group called Edge of Space Sciences, where we basically are for lack of a better phrase, a launch platform for scientific projects. A lot of schools use the group, and what they'll do is they'll launch a balloon. This thing starts out about 8-foot diameter or so here at the ground, with all of the experiments on board on a string, along with a whole pile of ham radio equipment. Goes up to about 100,000 feet, where the balloon is absolutely massive. It bursts, and then the whole thing comes down on a parachute, and we go out in the field and track it and find it. So it's an awful lot of fun. And I'll be working with that group, some of the leaders there, to get a good presentation put together for you guys.
It's kind of like when we used to teach diving. We used to show that we take a balloon down at 60 feet or something like that with newbies and things like that, and watch it blow up as it hits at the top. So done it. Haven't done it in the atmosphere, but have done it underwater. Any other comments, questions, or anything else for our little club net? Well, thanks to everybody. We will see you again next week. Of course, don't forget our Wednesday night club net and also our Monday night tech net. If there's anything that you want to see us do a presentation on, just send me a note at president@ncar.net. And I got a lot of specialists out there, and I'm sure that they'd be more than happy to do a presentation for you. So if that's it, thank you very much. You have a good day.
This presentation was brought to you by the Northern Colorado Amateur Radio Club. For more information, visit our website, ncarc.net. Thanks for watching, and don't forget to like and subscribe.